Now let's see inside the hidden dream space of image models. Right. So that may not say anything upfront, but we'll see to that. So by the end of this lesson, you'll be able to understand what latent space is. So that hidden dream space is simply the latent space that we're considering here. So we'll explain why image models use latent representations, describe how images are compressed into latent vectors, understand the role of encoders and decoders, and perform simple calculations involving latent vectors. So, I mean, when you hear vector, it's the normal vectors, if you've done something on vectors, so they are becoming useful here. So the maths behind AI are simply the maths you've always known, that I didn't know how powerful they've been. So things like the distance between two vectors, the midpoints of vectors, and things like that actually come very handy in this place. So visualize latent spaces using Python. So if you know nothing about vectors, I have a playlist on vectors which you want to check out. So just get onto my channel and click on playlist and scroll down, you find vectors there. In fact, everything that backs up AI, every math behind AI has been treated, at the basic level. So here we are just saying the core up, how do you really play into the whole idea of AI? So you'll be able to visualize latent spaces using Python and explain how latent spaces enable image generation. The introduction. When we ask an AI to generate an image, such as a futuristic city floating above the clouds at sunset, I think I want to practicalize this like I did with a red car the other time in a video, like I think two videos before now. So now I'm going into ChatGPT. That so far that's my favorite AI. Of course, a lot of people talk about Claude and how powerful it is. I agree, but I've not, I'm just used to ChatGPT for now. So a futuristic city floating above the clouds at sunset. We've talked about the whole idea of the future diffusion. I mean, forward diffusion. So what is happening right now is forward diffusion. So you have noise all over the place, and then, you know, at the end of the day, the noise is removed gradually until you then get what exactly you have described in the prompt. So, like we already know, ChatGPT doesn't understand this English you have spoken here, but the English, this prompt is broken down into tokens, and then those tokens are assigned vectors, and all of that happens so fast. And at the end of the day, so there's embedding and it goes through layers of neural networks, and then it finally generates this beautiful picture of a futuristic floating city, like that, a futuristic city floating above the clouds at sunset. So that's exactly what we now have right there. So it starts with an image where you cannot pick anything out, and then the noise is gradually removed to get what we finally have. So when we ask an AI to generate an image such as a futuristic city floating above the clouds at sunset, the AI does not immediately begin drawing pixels, right? So instead, it first imagines the picture inside a hidden mathematical world called the latent space. So this invisible space is where modern image generation models perform most of their reasoning. Rather than storing every individual pixel, the model represents each image as a compact collection of numbers called a latent vector. So the whole process of tokenization, embedding and everything, you have the whole latent vector thing going on. So every generated image begins its journey inside this image representation before being transformed into the final picture that we see. So understanding latent space is one of the keys to understanding modern image generation systems such as variational autoencoders, VAEs, generative adversarial networks, where you do so, yeah, you add noise and remove it. So it's more like you have somebody is drawing a picture, the other person is trying to remove parts of it that may not make sense. Like that. That's the idea of adversarial. So generative adversarial networks, and then we have stable diffusion and DALL-E. So question, what is latent space? So a latent space is a lower dimensional mathematical representation of data. So by the time you do tokenization, when you break your prompts down into tokens and assign them vectors and and do the whole embedding thing, you have a lot of numbers to deal with. But latent space helps you to compress that to make calculations easier. So latent space is a lower dimensional mathematical representation of data. Instead of representing an image by millions of pixel values, a neural network compresses the image into a much smaller vector that preserves the important information. So the word latent means hidden. So hidden space, kind of. So you have the feature space where you have the actual features, like which is pixel, which are pixels in this case. But the hidden space, the latent space now makes calculations easier. Therefore, latent space is the hidden feature space learned automatically by a neural network during training. So every point inside the latent space corresponds to one possible image. Now, images that are visually similar usually occupy nearby locations in this space, while very different images are located farther apart. So that was the same kind of thing we saw when we talked about what you're interested in is the generation of text. So dog and cat will be close by. Dog, cat, leopard, lion, and all of these things. They'll be closer together than aeroplane, car. So aeroplane and car will be closer together, in the whole embedding thing, which is automatically done by the model, by the way. So images that are visually similar usually occupy nearby locations in this space, while very different images are located far apart. Now, why do we need the latent space? Suppose we have a color image with dimensions 512 by 512 pixels. Since each pixel contains three older channels, red, green, and blue, then the total number of pixels will now be 512 by 512 times 3. So you have 512 by 512 for each one. So you don't do that in three places. That's 786,432. So that's just that. So processing nearly 800,000 numbers for every image is computationally expensive. So instead, an image model learns to compress the image into a much smaller representation. For example, these 786,432 pixels can be compressed into 512 latent variables. Although only 512 numbers are stored, they retain most of the information visually, only they retain most of the important visual information contained in the original image. So imagine the gap between 786,432 pixels to 512 latent variables. So this 512 captures the most important parts of this 786,432 pixels, because some of the pixels there are not as important. So once you get the key features, the rest can be made up for. And that is exactly why sometimes you get an image that is not as good as you would have it, but it looks like it, but not quite close. So that's what is going on there. Then we talk about compression ratio. Suppose an image contains 786,432 pixels, like we said before. So suppose an image contains 786,432 pixel values and is compressed into 512. 512 latent variables. The compression ratio then becomes 786,432 divided by 512, which is 1,536. This means the latent representation is 1,536 times smaller than the original image representation. So this is saving you a lot of space, a lot of compute, and all of that. So what does a latent vector look like? After passing through an encoder, an image might become something like this. You have Z, so it can become something like this. So these are different numbers in the embedding of the image, right? So it can just be like maybe, yeah, a very nice way, which we saw in one of the most early videos, is maybe you have an animal, and you want to talk about things like skin, maybe skin color, if you have skin color, you have, say, whiskers, you have, say, what else? Say eye color, if you like, eye color. What else? Say whether they have fur and all that. So you now come and say for dog now, okay? Dog, the skin color. So maybe let's just say the skin color is say brown. So and we say in our lettering, in our embedding, we can say brown is 2, just randomly, right? Then for the dog, dog have whiskers, right? But maybe we can just say, or to what level do they have whiskers? Or we can even do it on a kind of scale. We can do like a scale thing, right? So we can do scale, say from we can even use uh we can do a kind of scale thing, right? I mean, you can come up with any kind of embedding. So dog now, maybe dog, you can say dog is 3, or we can do the decimal thing also, you know. So let's say dog is 1.8, 1.8, 1.8. For whiskers now, let's just say that's 0.2. Then eye color. So eye color, we just assign values to some of this in 7.0, and 4, we say 2.4. So we have a scale that makes that happen. And then you have cat now. So then you say cat is like so cat and dog, the skin color can be a bit not so close. So in that case now maybe you just assign a value like 0.1 here. So for whiskers, the cat has whiskers. I mean, just do your kind of scaling. Let's say this is 3.0, and this is 4.1, and then this is 7.2. So you just go on like that, like that. Let's say we now have lion. So skin color, the skin color of a lion can be close to that of a dog. It depends on whatever the kind of dog. So let's say this is now 1.32, and then for the whiskers now, let's say this is 0.25, and then for eye color, we say it's 5.0, and then this is 6.1. So something like this now. So it means that the embedding for the dog is 1.8, comma 0.2, 7.0, 2.4. That's for the dog. For the cat now, the embedding, of course, this embedding, you don't do it manually. The model automatically does it. It just learns it from the data given to it. So you don't do it manually. But this is the idea going in the background. That's basically why I'm showing this. So for lion now, you have 1.32, 0.25, 5.00, and 6.10, like this. So these are the embeddings for each of these things. So that's exactly the kind of idea uh, there for the whole embedding thing that we've been talking about. So after passing through an encoder, an image might become z equals minus 0.82 and 1.25. So this is talking about different dimensions of the image. So this collection of numbers is called the latent vector. So these things I showed you here, they're actually the latent vectors, like that. So latent vector. So unlike pixels, these numbers do not directly represent colors. Instead, they encode abstract information learned automatically by the neural network, such as object shape, the texture, the lighting, the viewpoint, the background, the artistic style, the facial expression, and many other hidden visual features. So the model discovers these features automatically during training without being explicitly told what dimension each dimension represents. So, but I've just used this explanation now to tell you the kind of idea the dimensions can be about. So mapping images into latent space now. The first neural network is called the encoder, right? The first neural network is called the encoder. Its job is to compress an image into its latent representation. So you have an image, and then this one helps to compress it. So it has its number of pixels in there, thousands of millions or even billions. But then this encoder now helps you to reduce it to the most important part, just like that 786,000 thing that became 512. Mathematically, you have z equals f of x, where x is the original image and f is the encoder. So you can say f is a function that turns the original image into a latent vector, basically. So z is the latent vector. So you see mathematical function idea coming here. So the function is the encoder that turns the original image into a latent vector. So instead of remembering every pixel, the encoder remembers only the essential information needed to reconstruct the image. So how do you then recover that image? So recovering the image now, a second neural network called the decoder. So encoder projects the image onto a latent vector while the decoder reverses it, just like in the case of forward diffusion and backward and reverse diffusion. Forward diffusion, which adds noise to an object, and then reverse diffusion, which removes the noise to reveal the object itself, the clear image. So a second neural network called the decoder performs a reverse operation. It reconstructs an image from the latent vector mathematically x cap now. So it's like you're now taking you're getting your x back from here. So in that case now, getting x back is like taking you're now taking f inverse. So f inverse of z equals f inverse of f of f. So you then end up having your x back. So you have x cap is now a function. That f inverse is now a function of z. So after recovering the image, a second neural network called the decoder performs a reverse operation. It reconstructs an image from the latent vector. Mathematically, you have x cap equals g of z, where g is the decoder now, and is the z is the latent vector, and x cap is the reconstructed image. So the reconstructed image should closely resemble the original image. So we see a very simple case of inverse operations here, and which is an idea in mathematics. So then let's look at the encoder decoder architecture. So encoder projects an image to the latent space, and then decoder reconstruct the image from latent space. So the complete image reconstruction process can be summarized as this. So you have the original image, right? An encoder works on it, and it's projected into the latent vector, and then a decoder then works on it later after all the math has been done, and the reconstructed image is obtained. During training, both the encoder and decoder learn together so that the reconstructed image becomes as close as possible to the original image. So at the end of the day, you can get something as close as possible to the original image you have in mind. Then we talk about the reconstruction loss. Uh, so the quality of reconstruction is measured using a loss function. How close is the reconstructed image to the original image? So a common choice is the mean squared error, which is which is the norm of x minus x cap raised to power 2. That's the absolute value of the difference between the reconstructed image and the expected image, all raised to power 2, where x is the original image and x cap is the reconstructed image. The objective of training is to minimize this loss. So a smaller loss means the reconstructed image is more similar to the original image. See an example here. A grayscale image has dimensions 64 by 64. Since grayscale, once you hear grayscale, you work with it directly. So since grayscale images contain only one channel, the total number of pixels is 64 by 64, which is 4096. Suppose the encoder compresses the image into 64. So from 4096 to 64. So find the compression ratio. Of course, we know that's just going to be 4096 over 64, which is at 64. So the compression ratio is simply 64. So the compression ratio is the total number of pixels divided by the um the compression. So you have 4096 over 64, which is 64. Therefore, the latent representation is 64 times smaller than the original image, while preserving most of the useful information. That's talking about compression ratio right there. And then we come to similar images having similar latent vectors. Just like what I okay, I mean, we've been talking a lot about cat and dog being very similar. A cat and dog are more similar than a cat to a car to a car and a dog, right? So suppose two cat images are represented by Z1 1.2 0.5 minus 0.8 and Z2 1.4 0.6 minus 0.9. So maybe they only vary in some things. Maybe a cat is one is black and white and the other one is just white. That's why these dimensions will vary. Since the vectors are close together, as you can see, the two images are likely to look very similar. So this is one of the most important properties of latent spaces. Nearby points usually correspond to similar images. So how do you measure the similarity then? There are many ways of measuring similarity. One of it is the Euclidean distance between two latent vectors, which is basically the distance between two vectors that we know. So that's square root of z11 minus z21 squared plus z12 minus z22 squared plus z13 minus z23 squared. Smaller distances indicate more similar images. Larger distances indicate more different images. Example 2 now. Consider Z1 is 2, 3 and Z2 is 5, 7. Compute the Euclidean distance between these two vectors. So it's more like the normal vector computation we know. So the distance then is D equals square root of 5 minus 2 all squared plus 7 minus 3 all squared. And that is equal to 5 minus 2 squared, that's 3 squared, which is 9. 7 minus 3 is 4. 4 squared is 16. So that's square root of 9 plus 16, which is square root of 25. And the answer is 5. Therefore, you can say that the two latent vectors are 5 units apart inside the latent space. That's how apart they are. So if you have another vector that is not as close, then you have the distance bigger than that. So that can help the computer to know that, oh, these objects are closer together than these other ones. Although latent spaces often have hundreds or even thousands of dimensions, we can visualize simplified latent spaces using 2 dimensions. In a 2-dimensional latent space, each image is represented as a point on a plane. So images with similar characteristics tend to cluster together, while dissimilar images appear farther apart. So visualizing latent spaces helps us understand how neural networks organize images internally. Now we talk about creating random latent vectors. So to better understand latent space, let us generate a collection of random latent vectors. Each row below represents one point in the latent space. Imagine this now. You want to generate 100 random latent vectors. You want to generate 100 random latent vectors. So you have latent vectors now being equal to np dot. So you take the random function is coming from numpy, and then rand n is telling you the dimension of the vectors. So this is 100 by 2, a 100 by 2 latent vector now. So, and here you are trying to retrieve uh, just 20 of all that. So you have, so you now have a 20 by 2. So the 100 by 2 is available, but you are retrieving only the 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you have 20 by 2. So you have two columns like that. So we can generate random vectors like this. Now, because there's no seeding here, you can see that each time I run it, the values will change. Each time I run this, the values will keep changing. So take note 1.7 minus 1.55 minus 0.57 minus 1.4. So by the time it runs again, you're going to get totally different answers because these are, yeah, you can see the values have changed. And that is how we do the whole seeding thing that that we do sometimes, right? So, um, so the explanation, the function, this function we have here, this function, of course, we can have the whole of 100, right? If I put 100 here, we can retrieve all of it. If I put 100 here, so you get all of the latent space vector coming out like that. So that's very possible. So, but let me limit it to 20 like this, and then it keeps changing. So, so that helps us to see them. So in the explanation, the function np.random.rand n, that function 100 by 2 creates 100 latent vectors, each containing two latent variables. So maybe skin color, eye color, whatever two variables you may want to talk about. So these vectors simulate the hidden representations that may be learned by an image model. In practice, image generation models often use latent vectors containing hundreds or even thousands of dimensions instead of only two. And that is why we can get the kind of accurate results we get sometimes. So most times, in fact. So we can visualize these latent vectors using a scatter plot. So each point represents one image in the hidden latent space. Right? So here now you have import matplotlib to pyplot, then you have PLT figure. So the figure is a 7 by 7 one. So you have the latent vectors, you have the latent vectors in two dimensions now, one set against another. So this is one latent vector one, latent vector two with alpha 0.7. So we now have them in two dimensions now, latent dimension one, latent dimension two. So each row, I mean, each column represents a dimension. That's what we mean. So, and that's exactly what we are plotting here now. So each point represents one image in the hidden latent space. So we run this now and see what we get. So we have latent dimension one here and latent dimension two like that. So this is the compression of all of the what would have been the whole image that has a whole lot of pixels. So the scatter plot represents a simplified latent space. Each point corresponds to one image representation. In real image generation models, each point represents one possible image. Nearby points correspond to similar images. Distant points correspond to different images. So if this were to be one image, so it means that the image here looks closer to this than maybe to the image here or uh, to the image here. So, but this one is still closer to this than this one, and maybe an image that is at this point. So the closer together the points are, the closer the more similar those images are. So, although this example uses only two dimensions, modern models often use latent spaces with 128, 256, 512, or even several thousand dimensions. So, visualizing the real image data then, instead of random vectors, we can visualize the latent representations of real handwritten digits. So the scikit-learn digits data set contains images of handwritten numbers. So we will reduce their dimensions using principal component analysis to obtain a simple two-dimensional latent representation. So PCA is a very popular procedure that is used to for dimensional reduction, dimension, yeah, dimensional reduction. Yes, I think I talked about that a lot under machine learning with EJD, where I talked about some procedures like that. Dimensional reduction is actually a machine learning a machine learning process that you get to see things like PCA, I think TNSE and all of that, UMAP, variational autoencoders and all of that. So here we're working on digits now. We're working on handwritten digits. So from scikit-learn dataset to import load digits. So these digits now we're going to see them. In fact, let me see if I okay, let me see if I can print the digits. Let me see if it's possible to do the print. Print digits now. So you can see all the digits. Okay, I think okay, this should work. Digits. Okay. So X now that'll take the digits data, and PCA, principal component analysis, is breaking it all down, and then you have it is transformed into latent space, and then you have the visualization of the latent space here. That's what you're going to see on the graph. So the whole thing is totally different from what you see here. But let me just run this to see what happens. So it might take a bit of time because okay, now you can see all the images now. This is the embedding of the several images that like that. So we haven't seen the original images, but these are their embeddings like this. So this is optical recognition of handwritten digit data sets. These are their vectors, their embeddings in all the dimensions in which they come. So yeah, I think this can go now. Since it's all embeddings we are seeing. So instead of that now, we can then put them in we have the two latent dimensions, latent dimension 1 and latent dimension 2. And this is exactly what we have here. So you have latent dimension 1 and latent dimension 2. And that tells us about the digits, right? So if you see the blue ones, that talks about digit 0. If you see the orange, is this orange? I think so. Something close to orange. Those are the digit 1, like right here. So this is 0, 1, 2. We have 2 clustering somewhere around here. 3 is somewhere here. 4 is somewhere around here. 5, you have 5, scattered around this place. Then you have 6 around here. 7, that color is somehow, but I think yeah, I can see some of 7 around here. Then 8, you have some of them around here. And 9 around this place. So that is latent representation of handwritten digits now. So there's a lot of them, but then they are able to be compressed like that in latent space. The observation, notice that digits with similar shapes tend to appear close together. Okay, let's see. 3 and 8 seem to operate together, right? So you should be seeing red and this together. So we have a lot of red and green. Okay, 2. Does 2 look like it? So you have red and so you have some 8. They are close, a bit close by. So okay, let's even see here. So this is 3 and 2. Okay, 3 and 2 kind of look alike sometimes. No, do they really look alike? The first part, right? So you have 3 and 2 here. Then around here you have 5 and 6. Okay, something like this. You have 0, 0. What does 0 look like? You have 6 here. Okay, maybe a part of it, the bottom part of 6 looks like 0. Then you have 8 around here, and then you have 5 around here like that. So note that digits with similar shapes tend to appear close together. For example, many zeros cluster together, many ones cluster together, many sevens cluster together. Okay, that's basically the idea. So zeros cluster together, ones cluster together, and all that. So this demonstrates one of the fundamental properties of latent space. Similar images are mapped to nearby points. So let's talk about latent space interpolation. One fascinating property of latent space is that we can move smoothly from one image to another. Suppose ZA represents one image and ZB represents another image. Any point between these two vectors often corresponds to a meaningful intermediate image. So we can move smoothly, like that. So you see, we have this is 0 here, okay, and we have 1 here. Then we have green here. We have 4 here. We have 5 here. So you can see even border lines. You have 5 here. Then you have 6 here, 7 around here, and then you have 8 still around 7 there. Okay, yeah, this is 7 around there, 8, and then 9, like that. So similar images are mapped to nearby points. Now, latent space interpolation. Okay, any point between these between any two vectors often corresponds to a meaningful intermediate image. Now, talking about linear interpolation, the simplest interpolation is linear interpolation. The interpolated latent vector is z of t equals 1 minus t z sub a plus t z sub b. So that's some so in convex, when we talk about convex optimization, we have this kind of thing here. So you have interpolated latent vector z of t equals 1 minus tz sub a plus tz sub b, where t lies between 0 and 1. Now, when t is equal to 0, we obtain the first image. When t is equal to 1, we obtain the second image. Intermediate values produce gradual transitions between the two images, basically. So that's what the linear interpolation is about. So example here, suppose z is has dimension 2, 4, and ZB has dimensions 8, 10. Find the midpoint between these two latent vectors. Of course, it's more like finding the midpoint of two vectors that we know normally. So the midpoint corresponds to t equals half, as we know, based on the formula. So the midpoint corresponds to half. So in that case now, therefore, we can say that Z is half ZA plus half ZB. Following the formula, that's 1 minus half. T itself is half. So we then have, so that's half ZA plus half of ZB. So what is ZA? 2, 4. ZB is 8, 10. So half of ZA, that's 2 plus 8. So that's between ZA and ZB. So 2 plus 8, that is 10 divided by 2, that's 5. Then the other part, 4 plus 10 is 14 divided by 2, you have 7. Therefore, the midpoint is 5, 7. Just like when you look for the midpoint of two vectors, the decoder would usually generate an image that shares characteristics of both original images. Now, talking about interpolation with Python now, we have the following code generates intermediate latent vectors between 2 points. So you have, you import number as NP, right? Because array is going to come from that. And you have Z1 is 2, 4, Z2 is 8, 10. So for T in link space 0, 1, 6, right? So T is taking values here. So you now have Z equals 1 minus TZ1 plus TZ2. Then you print. So see, when T is equal to 0, the other time we dealt with T being half, right? When T is 0, nothing has changed. So you have 2, 4. Then when T is 0, see what's happening here. Because T is 0, so 1 minus 0, you have only ZA. So ZB is gone. And that is why only ZA remains there. You have 2, 4, like this. So that's why you have 2, 4. When T is 1, it preserves the other vector. So at t equals 1 minus 1 is 0. So the first vector goes and the second vector is preserved, and you have h10. So you can now say a transition. So every other thing between 0 and 1 is a transition in between 2, 4 and h10. So at t equals 0, you have 2, 4. At t equals 0.2, you have 3.2, 5.2. At t equals 0.4, you have 4.4. So this is gradually increasing towards 8, and this is gradually increasing towards 10. So everything between 0 and 1 is transitioning from the first vector to the second one. So these vectors move smoothly through the latent space. In a trained image model, each intermediate vector would generate a corresponding intermediate image. Then we'll talk about random sampling in latent space. Now, one of the most remarkable ideas in modern image generation is that we do not always need an existing image. Instead, we can simply generate a random latent vector. So a trained decoder can transform this random vector into a completely new image that has never existed before. And that is one reason why AI can generate unusual things. For instance, I may want to say generate a flying, a flying, okay, let me just say a flying lion with eagle wings. A flying lion with eagle wings. So this one is going to have features from both lion and eagles, right? So, I mean, so there's nothing like that in reality, but so AI can take the idea of a lion and the idea of an eagle and couple things together to generate images that do not normally exist. So And that's why in the age of AI, your imagination can run wild. You can create whatever you like. So let's see what our flying lion with eagle wings will be looking like. A flying lion with eagle wings. So so you're going to have a transition between lion and eagle. Voila, we have it now. Yes. So a lion is flying, it has eagle wings like that. So that's exactly the idea here. So one of the most remarkable ideas in modern image generation is that we do not always need an existing image. So instead, we can simply generate a random latent vector. A trained decoder can transform this random vector into a completely new image that has never existed before. Now, a flying lion does not exist. A flying lion with eagle wings does not actually exist like that. So here now we can generate something random that's a one-dimensional latent space with 128 items like that. So we can have all of that. So that's exactly what we have here. So you can create something, you can unleash your creativity. Now, the command np.random.rand n128 creates a random latent vector containing 128 numbers, but we have only retrieved 20 of those numbers here, right? So because if we allow the 128 to go, it will show us all of the 128. So we can actually see everything. So this is only a one-dimensional vector because if you want more dimensions, you would have stated it here, right? So imagine if I said 2 by 128. Maybe that's going to give, yeah, okay, 2 by 128. So one stops here, another one starts here, like that. So those are the possibilities you can do. So you can just generate these things randomly. Okay, so the explanation here, okay, that command creates a random latent vector containing 128 numbers. A trained decoder interprets this vector as a meaningful representation of an image and generates a realistic picture from it. So this simple idea lies at the heart of many modern image generation models. So then we talk about image generation pipeline now. A simplified image generation pipeline is you have the random latent vector and you have a decoder and an image is generated from it. So instead of drawing pixels directly, the decoder converts mathematical representations into realistic images. So from random noise to images now, initially a randomly generated latent vector appears to contain no useful information. However, I mean, when you see this, when you see all this number now, it doesn't make sense to you, right? But there's a lot of information right there. Now, so from random noise to images. Initially, a randomly generated latent vector appears to contain no useful information. However, during training, the decoder learns how different regions of the latent space correspond to meaningful images. As a result, random vectors can produce realistic faces, animals, landscapes, paintings, and many other types of images. Now, why does this work? The decoder has learned the hidden structure of the training images. Instead of memorizing individual pictures, it learns the mathematical relationships among them. Therefore, sampling a new latent vector often produces a completely new image that still resembles the images contained in the training data. Then we have, now before I go further here, so I have this idea. Imagine I can upload a new picture onto this place. See what is going to happen. When I upload a picture, the picture doesn't show straight. It just shows plenty numbers first, and then later it generates the picture. So let me click on this. Like I'm talking about a normal picture that already exists, right? Let me see. Let me go to downloads. Um, Let me try to see. Can I get a picture of myself to show here? Okay, yeah, I think so. Okay. Yes. So imagine, just watch what is going to happen around here. So I upload this image now. So you can see it's an image I uploaded, right? But see all the numbers it has generated. See plenty numbers just for one picture. So imagine how plenty the number is. All the numbers and letters and everything. So those are like the codes for the picture I've generated. But if I click outside the box now, I'll get the image. So now I just watch. all these numbers now will just become picture. I click out here now. So we then get the picture I uploaded. It's far. Yeah. So this is the picture I actually uploaded. So that's the picture that gave all those plenty numbers, at that point in time. So that's the deal here. So that's what you have. So let's talk about applications of latent space. Latent space is one of the most important ideas in modern artificial intelligence. Once an image has been transformed into its latent representation, many useful tasks become easier. Instead of manipulating millions of pixels, we manipulate only a small number of latent variables. This makes image generation faster, more efficient, and more flexible. So application one, you have it in image generation. Perhaps the most famous application of latent space is image generation. Instead of providing an existing image, we simply sample a latent vector from the latent space, and a trained decoder then transforms this latent vector into a completely new image. So every newly generated image begins as a point inside the latent space before being converted into pixels. This idea powers many modern image generation systems. Then you have image editing. Latent space also makes image editing possible. Instead of modifying individual pixels, we modify the latent vector. So small changes to the latent vector may produce changes such as adding a smile, changing hair color, changing facial expression, changing lighting, changing age, changing artistic style. Because the edits occur in latent space, the generated images usually remain realistic. Imagine now, this picture I have the picture I just uploaded of myself, right? Imagine we can edit that picture. I just come over here and say some and do something funny. So imagine I have no suit on here, right? It's just a shirt on jeans. So um give me a nice suit. Give me a nice suit. I'm not wearing suit. Well, I just want AI to give me a nice suit, right? So let's see how that works. So that's the idea of image editing. So we all remember the days of is it no Photoshop, yeah, Photoshop and all of these things for editing images. So now AI has made the job way, 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 way better. Way better. So we have all of that. Now, can you see? So now I have a nice suit on. Though I wasn't wearing suit initially. And, everything remains intact, the way I made my hand and everything. So, and it looks very real. I mean, somebody can just see this and think it's actually a real picture. And those are that's the kind of thing, um, you know, uh, latent space has made possible. I didn't even ask for a tie. Now I have a tie on. So that's the deal. Right. So then we have image search. Image search becomes much more efficient in latent space. So every image in the database is first converted into a latent vector. So when a user submits a query, the query is also converted into a latent vector. Now the system then searches for nearby vectors instead of comparing millions of pixels. This approach is known as similarity search. So you can search for images. And I believe this is the idea Google Lens is based on. So if you have any image, just snap it with Google Lens, and then you see it can help you locate that kind of image. Maybe if you want to buy a type of a particular thing, so you can just take a shot of it with a Google Lens, and then you can find it. Then latent space provides an efficient way to compress images. So image compression is another thing, right? So instead of storing every pixel, we store only the latent vector. When needed, the decoder reconstruct the image, although some information may be lost. The reconstructed image often looks very similar to the original. So this principle is widely used in autoencoders. So here now it wasn't like a compression, like it was a change of the background still looks intact. Everything just looks perfect, with a suit I don't have that I've not even seen before. So that's how this whole thing goes. So this principle is widely used in autoencoders. Then you have variational autoencoders. Now another application of latent space is in variational autoencoders. Variational autoencoders organize the latent space so that nearby points correspond to meaningful images. Instead of learning arbitrary latent codes, variational autoencoders encourage the latent vectors to follow a probability distribution. Typically, Z is normally distributed with mean 0 and variance I. So where n denotes the normal Gaussian distribution and the mean is 0, and this is the covariance matrix, that which is the identity matrix. Because of this regular structure, new images can be generated simply by sampling random latent vectors like that. So when I say give me a suit and all that, so it would simply sample other random latent random vectors and then create something like a suit for me. Okay, let me just say change it to Agbada. I hope it understand what Agbada is. Change it to Agbada like that. So we have the magic coming. I hope it understand what Agbada is though. I think it should. Let's see what it comes up with. Like that. Making the first draft. So this is the whole process of denoising. It starts with noise and then it starts removing the noise gradually. And then finally we get the pixels. Then now it's polishing the details after having removed all the noise. Finishing up now, making sure everything works good. And then adding final touches. Then we should be ready to see me in Agbada, which I don't have. One last tweak. Let's see what we get. So this whole process is still the whole denoising process, making sure the edges are right and there are no earlier versions of AI, right? You can see if you wanted it to do this, you probably have three hands or two or five legs and different kinds of I think what is that thing called now? We came across the name in one of our earlier videos. Um so that error, I'm trying to remember. Of course, it's hallucination in some cases, but for images, it has a particular. Now you see me in full Agbada. Interesting. Very good. The posture the same, everything the same, but now I have an Agbada on like that. So that's so cool. So we have all of that. So, with generating images via a variational autoencoder, the image representation process is straightforward. Sample a random latent vector, feed the latent vector into the decoder, produce a completely new image. Although the sampled vector has never been seen before, the decoder can still generate a realistic image because it has learned the structure of the latent space during training. That's exactly what is happening here. This is the original picture, and then now this is me wearing suits with the same posture, and then this is me wearing Agbada with the very same posture, not because it has seen any of this, but because it can work on latent vectors to get to make anything happen. So here we have a very simple latent vector like that, which we've seen a couple of times. So although the sampled vector has never been seen before, the decoder can still generate a realistic image. So like we have with the suit and Agbada thing. Then we have generative adversarial networks, GANs. So GANs also use latent vectors. A random latent vector is provided to the generator. So you have a generator. So the generator transforms this vector into an image. So you have the generator receives a latent vector, it makes it into an image. Another neural network called the discriminator determines whether the generated image appears realistic. So in all the process of cleaning up, for GANs, it would have been like the image is generated, and then you have the discriminator trying to say that, oh, the edges here are not sharp, the face texture is not good enough. So, and that's why it is adversarial, right? So you have the generator generating the image, you have the discriminator trying to say, no, this doesn't look realistic. So through this competition between the generator and the discriminator, that's how we say it is adversarial. Through this competition, the generator gradually learns to create highly realistic images like that. So it's more like you have somebody is doing something and somebody else is there to say, no, this is not okay. It's more like when on a site, right? When people are you have security people outside of the work site. So as maybe a truck is trying to move out of the site, they are there to say, okay, move this way, or maybe it's a difficult place to move out of, to drive out of, right? So you have people there saying, oh no, turn your hand to the right, turn to the left, and all of that until the person can drive out safely. So then we have diffusion models, which we've been talking about a lot. So that modern diffusion models also rely on latent representations. The generation process begins with random noise, which we've been talking about. Then the model repeatedly removes noise while moving through latent space until a clear image appears. Instead of generating an image all at once, the image gradually emerges over many denoising steps. So stable diffusion is one of the best known examples of this approach. So advantages of latent space now. Latent space offers many important advantages. These include compact image representations, reduced memory requirements, faster computation, smooth interpolation between images, efficient image generation, effective image editing, similarity search, improved image compression, denoising capabilities. These advantages explain why latent spaces have become central to modern image generation. And then we, of course, have some limitations. Despite its many advantages, latent space also has limitations. Some important challenges include latent dimensions are often difficult to interpret. Training requires large data sets. Training can be computationally expensive, of course, because it requires large data set. Poorly trained models may produce unrealistic images. That's why when the whole AI thing started, you could see all kinds of funny pictures when images are generated. Generated images may inherit biases present in the training data. Researchers continue to develop improved latent representations to address these challenges. As it stands today, AI has so much improved that have hyper realistic pictures, and people may not be able to tell what is AI and what is not. So, in summary, in this lesson, we studied the hidden mathematical world called the latent space. We learned that images are compressed into latent vectors, and encoders map images into latent space, and then decoders reconstruct images from latent space. Nearby latent vectors usually represent similar images. Interpolation creates smooth transitions between images, and random latent vectors can generate entirely new images. Latent space forms the foundation of many modern image generation models, including variational autoencoders, generative adversarial networks, where you have a generator and a discriminator working together to generate realistic images. And then you have diffusion models like stable diffusion. So we have our practice problems as usual, as you can see questions 1 to 8 clearly in this place now. You can see questions 1 to 8. I get to solve 2. I think one of the 2 I'll be solving is question 7. Then I'll solve 9. So question 7 says an image contains 784,432 pixel values is compressed into 1024 latent variables. Calculate the compression ratio. That is easy peasy. Just divide 786,432 by this, and then you get the compression ratio. So then we see questions 8 to you can see up to question 8 to 12 here. So I'll be answering question 9 again. That simply talks about Euclidean distance between two latent vectors, which is pretty straightforward. So you can see 8, 9, 10, 11, 12. Then you can see 13 to the end here. So you can see the rest of the questions right here. So let's go ahead and solve problem 7 and 9, and then this will be over. So I have problem 7. It says an image containing 786,432 pixel values pixel values pixel values is compressed into 1024 latent variables. Calculate wow. Okay, calculate the compression ratio. And then we have the solution. The compression ratio is computed as compression ratio equals number of original pixel values, number of original pixel values all over number of latent variables, number of latent variables. So that tells us that the compression ratio now is 786,432 divided by 1024, which is equal to 768, basically. So this tells us that, so you can say, so the image has been compressed. Image has been compressed by a factor of 768:1. This means the latent representation, is 768 times smaller than the original image, representation, while preserving its most important features, Okay, so we go on to problem 9. So for problem 9, it's a vector thing, straight to the point. Given the latent vectors, of course, we know that latent vectors are of several dimensions, but just for explanation's sake, given the latent vectors Z1 equals 2, 5 and Z2 equals 8, 13, calculate the Euclidean distance between between them, right? Between them. Okay, so 2, 5, 8, 13 keywords. So here we can have what should we have now? Okay, let's go for this solution. The Euclidean distance between two vectors is d equals square root of x2 minus x1 squared plus y2 minus y1 squared. So based on what we have, right, we have z1 to be 2, 5, that's x1, y1. Z2 is 8, 13, that will be x2, y2. So in all, then we can have Euclidean distance d to be square root of x1, x2, y2. So x2, x2, x minus x1, that's 8 minus 2 squared plus y2 minus y1, that's 13 minus 5 squared. So that d now is equal to square root of 6 squared plus 8 squared. So the distance between the two vectors now is square root of 6 squared is 36, 8 squared is 64. So that d now is equal to square root of 100, and then d is equal to 10, like that. So d is 10. So what does this represent? So we see that the Euclidean distance between the two latent vectors, is 10. And what does that mean? This indicates that the two image representations, are they are actually 10 units apart in latent space. They are 10 units apart in the latent space. So with that, we come to the end of this interesting video talking about latent space, which helps, you know, when we talk about image generation. So it helps to reduce computation. That's why it is the hidden dream space for images, for image models. So let's see the questions again. You can see questions 1 to 8 here clearly. So I did 7. And you can see questions 9 to 14 here clearly. Okay. You can see question 9 to 14 here. I did 9, yeah. I mean, to find midpoint, it's 1 over 9. 1 plus 9 over 2, that's 10 over 2, 5. 4 so 5, 7. I think it's the same thing we saw in the body of the explanations too. So you have 15 to the end here. Let me know how helpful this is for you. And if there's something else you like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is exactly the time to do that. Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges. It gives you special privileges. That you find out when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.